Picture this, you're at your favorite coffee shop, you look away for literally 1 second, and boom, someone grabs your laptop and bolts. It's a classic physical digital heist. So what are they actually going to find? Welcome to This Explainer. Today we're going to break down exactly how modern hardware, specifically through mechanisms like the Trusted Platform Module and BitLocker, uses advanced cryptography to protect your data from physical thieves. We're diving deep into the trusted hardware material to see how this all works in the real world. Okay, let's dive into this. Most of us feel pretty secure, right? We have a password to log into Windows. But let's completely shatter that illusion for a second. If an attacker has physical control of your device, your operating system password is, well, it's completely meaningless. They don't even need to guess it. They can literally just unscrew the back of your laptop, rip out the physical hard drive, and plug it right into their own computer. And without further protection, all your documents, your photos, your corporate secrets, they're just sitting there, wide open, like an unlocked book. To understand how we actually stop this physical hack, here's our roadmap for today. Number 1, we'll look at the physical device theft threat. Number 2, shrinking the trusted computing base with the TPM. 3, measured boot and the chain of trust. 4, sealing and unsealing. 5, BitLocker sector encryption. And finally, number 6, remaining vulnerabilities. All right, section 1, the physical device theft threat. We're stepping away from network hackers here to focus strictly on physical adversaries. So the fundamental difference between software threats and physical threats all comes down to the boundary of your defense. With remote network attacks or malware, your operating system is basically your fortress, right? Your firewall and antivirus are working overtime for you. But in a physical attack, all those software defenses are completely bypassed. Like we just talked about, an attacker could physically remove the disk. Or, even sneakier, they could just leave the disk inside, plug in a USB drive loaded with Linux, boot your laptop from that USB, and freely read your hard drive right there on the spot. No network required. Now, the most obvious solution here is to just encrypt your entire disk. But as Professor Nikolai Zeldovich from MIT puts it, encryption reduces one security problem to, hopefully, a smaller security problem. Encrypting the disk absolutely is the best defense because if an attacker pulls the drive, all they're going to see is a giant mountain of random gibberish. However, it creates a new, smaller problem. Where on earth do we safely hide the encryption key? If we use a password as the key, users are just going to pick weak ones. If we put it on a USB flash drive, people will literally just leave it plugged into the laptop for convenience, which means the key gets stolen right along with the laptop. Total fail. Let's move to section 2 and see how this builds, shrinking the TCB and the role of the TPM. In hardware security, we have this concept called the Trusted Computing Base, or the TCB. This is the absolute minimum hardware in a system that we absolutely must trust for the whole thing to be secure. The secret here, we have to shrink this TCB down as small as humanly possible. We're talking only trusting the CPU and main memory. That's it. And most importantly, we strictly kick the physical hard drive out of this trusted circle. The hard drive is now treated as compromised enemy territory. Since we can't trust the disk to hold the secret key anymore, the industry came up with the Trusted Platform Module, or TPM. This is a tiny, dedicated hardware chip that's permanently embedded right onto your laptop's motherboard. And it's designed to be highly tamper-resistant. You can basically think of the TPM as a strict bouncer or an ultra-secure vault built right into the system. Its main job is to stubbornly guard our disk encryption key and keep it safe from any unauthorized software that might be trying to boot up. Moving on to Section 3, Measured Boot and the Chain of Trust. But how does the TPM actually know when to release the key and when to keep it locked down? Well, the system uses a really cool process called measured boot. It works exactly like a relay race. When you power on your machine, the most basic part, the ROM, starts running. Now, before the ROM passes control, it reads the bootloader code from the disk, mathematically measures it, and records it. Then the bootloader runs, measures the OS kernel, and records that. Finally, the OS kernel does the exact same thing for the BitLocker software. Every single step mathematically measures the next step before handing over the baton of control. And this brilliantly illustrates the function of platform configuration registers, or PCRs. Remember those measurement records we just talked about? Well, they are safely stored inside the TPM chip, in these PCRs, using a one-way cryptographic function called a hash. This creates a permanent, sequential, and entirely uneditable hardware guest list. It details exactly what software loaded since the exact moment that laptop was turned on. All right, Section 4, the secret key, sealing and unsealing. So the TPM has two magic commands that make this whole vault mechanism work: seal and unseal. When we first set up our computer, we use the seal command. This tells the TPM to encrypt our disk key and tie it specifically to a certain PCR state, like, for example, the exact state of your clean, authentic Windows boot. When you restart the laptop later, the system asks the TPM to unseal the key. And here's the kicker: the TPM is incredibly stubborn. It will only hand over the key if the current PCR state perfectly matches the state when it was sealed. So if a thief tries to boot your laptop using a malicious USB drive, the software code is different, the PCR hash values change, and the TPM flat out refuses to unlock the key. No way, access denied. Which brings us to Section 5, BitLocker and hard disk sector encryption. Now, what's really interesting about this slide is the intense, almost crazy constraints engineers face to actually make this work on the disk. In modern cryptography, standard encryption doesn't just scramble data. It adds extra data, like a random nonce for randomization and a MAC check to detect if someone tampered with it. But for disk encryption, Windows rigidly treats the hard drive as exact 512-byte blocks. There is absolutely zero extra room, literally none. You have 512 bytes of plain text that must fit perfectly into a 512-byte sector on the physical hard drive without a single byte of space for extra security data. Facing these extreme spatial constraints, BitLocker actually uses some incredibly clever engineering hacks. First off, since they have absolutely no room for a random nonce, they just use the physical sector number of the disk itself. This means if an attacker tries to copy an encrypted sector from one place to another just to trick the system, it fails entirely. Second, because there's zero space for a MAC integrity check, they use something called a diffuser technique. This is designed so that if an attacker alters even one single bit of the encrypted data on the disk, when the system tries to decrypt it, that entire 512-byte sector basically explodes into a pile of completely broken, unreadable digital garbage. An attacker cannot subtly alter your system configuration to bypass the logging without destroying the whole sector. Finally, Section 6, remaining security vulnerabilities. Now, even though the math here is basically bulletproof, we have to come back down to the real world. The physical implementation can totally be the Achilles heel of this entire setup. A highly advanced attacker with physical access could try something called wire snooping. This literally means physically tapping the tiny copper wires between the CPU and the TPM chip on the motherboard to steal the key as it travels across. Or they might just let the system boot normally so the TPM decrypts the drive, but then plug in a USB with deliberately buggy drivers. This exploits a software vulnerability in Windows to get access after the fact. So the crucial point is, it's often not the hardware that defeats this security, but human convenience. Imagine all this intense engineering, the TPM, the 512-byte constraints, the PCR hashes. It's brilliant. But Microsoft knows users will be absolutely furious if their motherboard breaks and they lose all their family photos forever. So, by default, modern Windows actually backs up your BitLocker recovery key to your Microsoft Cloud account. That totally bypasses the hardware's physical security protocols. You've built this impenetrable physical vault only to automatically stash a spare key on a cloud server. In fact, authorities like the FBI have used this exact route of convenience, requesting keys straight from Microsoft servers when they can't crack the physical hardware. Which leaves us with a truly provocative thought. We've engineered near-perfect hardware, locking the front door with the most advanced physical cryptography available. But if the backup key to that high-tech vault is automatically saved on a server thousands of miles away, just how secure is that physical device in your hands right now? It's this incredibly delicate dance between user convenience and absolute physical data security. Definitely something to think about the next time you leave your laptop unattended. Thanks for joining us for this explainer, and we'll catch you next time.